got our trends. The second exercise, we went in and figured out what our trends would be. The next two exercises, we took those particular trends into the rock physics spreadsheet and figured out what the amplitude response should be. Then we went in and more recently, yesterday, we were extracting amplitudes, comparing those amplitudes to the expectation or the AVO response to the expectation in order to come up with what we thought our volume should be, and also we used the risk analysis spreadsheet and in terms of the comparison of the observed amplitudes to the expectation in order to come up with what we thought the risk should be, which were the wheels of fortune. And again, this is figuring out what things should look like. This is seeing what they do look like. You compare the two things, and then you can come up with the risk and what the particular volumes are. Okay? And so this is phase one. We've gone through everything in phase one now, and I'm going to be turning you loose shortly before lunchtime with respect to the lease sale example, where you can try it quite a few times in order to be able to compare different prospects to figure out which one you're going to bid on. Now, but before we do that, I did want to go and give you a bit of exposure in the course in terms of what is the next level. Because when we talked about volumetric estimation, we went around and we said there are quite a few different ways that the approximation of that simple model of a laminated sand shale mixture with the same shale on either side of it could be violated. And well, we do have methods to address this. I'm not going to go and, other than the spectral decomposition, you're not going to go, and the goal of this course is not to get you a point that you can do the analysis or that you understand all the nuances of the analysis. But I do want you to be aware that it exists and under what circumstances you should ask for it, and also if you do ask for it, what you will get, okay, in terms of a product. And first of all, when should phase two be used? And this should be your little checklist if you have an opportunity. First thing is that, do you have a complicated model that is more than this particular simple model that I've talked about? Are you going and are you risking multiple fluid contacts and want to know what, so that's more of a complication of the model, two contacts. Do you desire not only an estimate of the volumetrics, but a fair estimate of the range of what the volumetrics could be? Do you want a little bit more risk reduction? Okay, and you say, well, I always want risk reduction. No. I mean, if you go and the risk is already low enough, you're going to drill the well, and you have as much equity as you can have in that well, or if you reduce the risk a bit more, the expected amount of risk reduction wouldn't be enough to increase your equity, or you just can't increase your equity. You may not always want to go and reduce your risk a bit more. Do you have particular correlation in the rock physics? And you sort of scratch your head, well, what's that? Well, it really says that, and you sort of have to think of it, and there's a sort of a paper that we've ended up writing and putting in the leading edge. And in that paper, we sort of talk about trying to go and understand the difference between day and night by looking at the temperature, okay? Now, if you go and take a look at it, it isn't very good, right? If you look over a year, the day temperature isn't really that much difference compared to the nighttime temperature because of, you probably guessed it, it's seasonal variations, right? Okay, but if you end up looking at today's temperature versus tonight's temperature, there actually is a fairly good difference. Or in other words, that the uncertainty around what the particular temperature is ends up being much less, because today's temperature is very correlated to what tonight's temperature ends up being, okay? And there's an analog in that as you move from, let's say, basin to basin or one region to another, it's like changing seasons. But if you're looking at an area that's immediately sort of in the brine leg versus something that's in the hydrocarbon leg. That's more analogous of like going from today to tonight in terms of what the temperature is. And you scratch your head, okay, what does that mean? Well, it means that there's a local correlation in the temperature in the first case, okay, and in the rock physics in the second case when we're dealing with something local. And so that we can say that we don't know exactly what the compaction state is, but we do know the compaction state of the rocks immediately down dip of the contact is going to have to be very similar to the compaction state of the rocks up dip of the contact. I do want to say this is a very powerful assumption, and that if you're going into new venture areas, it's something that you should really keep in mind of whether or not you want to bring this in. Okay? Is that sort of clear to people, or? Okay. At least no questions. Okay. Okay. Does the particular rock physics vary as you move around your prospect, or does the compaction state vary significantly? Therefore, the trends should be aerially different. Okay. Do you have need for more complicated rock physics? Do you want to go and take into account sort of ways of bringing in the sorting? Or do you want to go and bring in explicitly effective stress changes that come from production or that you know from some of your basin modeling? Okay, if any of these things are of significant importance to you, you should sort of think about using the particular phase 2 analysis. I talked a little bit about this in the introduction. When we do this, we not only go and try to match the seismic data and get sort of a solution, but we actually go and try to adjust these complicated models so we get a range of solutions that are all consistent with the measured seismic to within a particular uncertainty. And here, each one of these little, what we call sort of spaghetti noodles, ends up being associated with the synthetic of one of the models that ends up being consistent with the particular seismic data to within the signal to noise level. Before the inversion, we just have a very rough idea of what's there, a very rough idea of what the, let's say, the net to gross would be. Afterwards, you end up getting more of an idea because you have to be consistent with the seismic data. And what happens is that if we look at one of these locations, and this happened to be fairly close to the original Sky Barrel discovery location, that the seismic data here is shown as the black wiggle shaded in. If you look closely, there's a little red wiggle that comes up to here and then only comes up to here. It's sort of shifted a little bit up. That ends up being the synthetic of the model we built before the inversion that comes off of, which is based off of the interpretation. And you can see because the top of loop ends up being sort of aligned with the, this actually is a negative kick because of the polarity that was chosen in the data. So this is a soft kick. You see, though, we allowed a lot of uncertainty in terms of where the top of the reservoir would be, and also the color shows the impedance, and that's related to the uncertainty in what the properties of both the reservoir and the bounding shale would be. After we go and said we have to make things consistent with the seismic data, you see that these models all look more like each other. And also, you can see where there isn't much uncertainty where the top of the reservoir is. There isn't much change in it as we go from each of these possible models. There's a little bit more uncertainty on where the base of it is. What's kind of interesting, it has detected that there is a layer above it which is of greater acoustic impedance than the shale above it or the shale below it. And so you can see here that even though overall that Sky Barrow is a fairly simple reservoir that is picking up this complication in terms of the bounding lithology being harder, but it also picked up the fact that it's not really certain where the top is, but it does feel that it's kind of, iffy on whether it's here or here, but eventually it does return back to the same value that is below the reservoir in this case, okay? So it's picked up this particular more complicated model, and you end up having the uncertainty associated with it. You can also see from here that we can therefore get multiple looks at what these net sand maps look like. Okay, I think that when most people look at this, they're a little bit astounded because every one of these is consistent with the well control, matches the well values where the well was drilled, and also each one of these net sand maps will give a seismic that will go and match the observed seismic to within the signal to noise ratio. Okay? And the thing which really does start making managers nervous, especially development managers, is these things don't look a lot alike. Okay? And that your particular development plan better be robust enough to be able to handle each of these particular equally likely physical realities, because they are likely, okay? In other words, that we've probably been, in many cases, by focusing on the most likely model, have been going and, probably have thought that the particular uncertainty around that model has been probably much less than what it probably should be. We also have a further process which comes up when we call the decoration step, because seismic resolution is this sort of, in this case, is about 10 meters in terms of what you can resolve. And it tells you how many, or sort of the fraction of thin laminations within here, and that's a net to gross, and this is colored according to the net to gross. But we know that the way things really look are these little, either your sand or shale here, and you end up having these laminations, but you know that the sum of the black has to be equal to the predicted net to gross that's coming from the seismic. But we also don't know, or we can go and ask the geologists, but in this case, they said, well, we really don't know. We sort of know these things tend to be about this thick, and so we can tell you about the average thickness. But we really don't know whether or not they're parallel to the edges or at some angle to the edges. And so that we ended up having two decoration styles, okay? One is modern and the other is going to be Louis XIV here, in terms of the way that you actually decorate it with these shales, okay? So given one of these sort of ways that the seismic scale will look like, you can go and we make it so that you can decorate these with sort of subseismic character so that you can go and do your flow simulation. And that I think most of you do realize that flow simulations are a couple things about them, okay? The first thing, okay, is that the particular flow simulations like to have these unstructured coarse grids in an XY sense, but they also like to have more vertical resolution by about a factor of 10 than is normally attainable from a seismic perspective. And so this is a way of putting that in, but this subscale or this decoration of these two styles can make a significant difference, because these are more likely to act as flow baffles with this Louis XIV style, or in certain cases absolute flow barriers if they're extensive enough. Okay?
Hey Mike, back to those net sand maps, how are each one of those net sand maps changed? I missed that part.
Okay, the way that they're changed is that if you take a look at these different models here, okay, that each one of these models have a different amount of net sand in this particular interval, okay? So we took a look at the amount of sand, okay, in all of these models and what the range was of the amount of sand that you could expect as you sort of changed and went across these models. And so what we then did was modify the amount of sand according to sort of the range of net sand that was predicted, okay, at this, across all of these models, okay? So for this one, for instance, we would have chosen this realization, this model. For this one, we would have chosen that realization, okay?
Doesn't that assume that they're uncorrelated? Sort of.
We actually build in correlation. We build in spatial correlation. I'll talk about that in a second.
Yeah, you mentioned that, these look very different, the different realizations, like the top one and the bottom one.
Yeah.
There's one part that says almost like 0 cent, but the other one says there's 35 cent.
Yeah, well, you see that there's actually less, you will see there's less uncertainty above the fluid contact than below the fluid contact, okay? And that comes about from a fairly good reason. It's a lot brighter above the fluid contact. Your signal to noise ratio above the contact is better. And the largest uncertainty is whether or not there's an aquifer there. But that's actually a fairly significant statement. There is uncertainty on whether or not you're going to have aquifer support on this. But go ahead.
It's just that I was confused. I thought that whether you have 0 cent or 35 cent is a huge difference. And the seismic data, I thought that's
Yeah.
You can
Yeah,
solve
well,
that.
there
You
isn't,
can
you'll see
solve
that there
that.
isn't as much variation here, okay?
That's part, yeah.
Okay, below here there is, but that's because the sands are relatively transparent here, even when there's brine in it.
That's that type of uncertainty.
It's an uncertainty.
I thought the uncertainty in seismic data is less than that.
Yeah.
Okay.
I guess what would be interesting, can you produce a graph of where the origin of the uncertainty in the net sand as a function of space? Because then you'd know where to drill.
I'll show that.
Ah.
Yeah, that's true. You're a very good straight man. Sort of setting up my jokes. Okay, this is our Reg-Jones diagram. I don't really want you to probably go through and understand all the nuances. It was prepared at the request of Mark Woodall here in the back, who asked, I want to know what the workflow looks like and where things go from and to. But there are a couple of things that I do want to point out to you. Major inputs into this are geology. We need to talk with our geologists. We need seismic data and imaging velocities. We also need well logs, okay? What the outputs of this are reservoir models with lateral correlation built in. And along the way, we do use our wave derivation program with uncertainty. We need to know the signal to noise ratio, because that's how you know how well that you need to match the seismic data. We use our program called delivery in order to be able to go and make sure things are consistent with the seismic data within the estimated uncertainty. We do have to go and build in the lateral correlation after the fact, and we do that in terms of the analyzer and the massager. We also go, if you go and build your model in Eclipse format with the faults, we do honor those faults and the unstructured grid that you have, and can put the results of the seismic directly back on the unstructured reservoir simulation grid. And we can give things like these uncertainty properties that you were talking about, uncertainties in something like net sand. We can give average, we can give how big it could be, how small it could be, and we can give certain realizations of what reality could look like. So you can have sort of 5 sort of models that sort of span what could be happening, and you should be prepared in order to be able to address. We do use the trends explicitly in the same exact functional formats that you were using for the rock physics. So this is reused information here. We do use a basic interpretation where you have good interpreted seismic horizons, we'll put in less uncertainty. If you use geology to go and phantom in some other horizons, we'll go and put those in, but with larger uncertainty since they're not based off of that. We do like having one reference in both surface, in both time and depth, so we can hang this model. And you'll see that we give you models in either time or depth, and we'll give you depth uncertainty associated with that. And we do end up using and like to use a sparse spike inversion in order to build this sort of framework model that goes into the inversion. I think those were sort of the major things in terms of what the sort of point out in terms of this sort of Reds-Jones diagram. But again, these are the petrophysical trends that we derived in one of, I think, the second exercise, first and second exercise. When we start going and doing this, especially as we move into a development sense, I think the particular mining people here could well find this of a bit of interest, is that we do explicitly bring in and build in the wellbore information. You see that we built a model in this case to do the inversion that had 17 different layers in it. This is Scarborough for the people that have worked this asset. This is, we ended up having seismic horizons that corresponded to the black lines. The red line is the fluid contact. The particular divisions were things that were probably seismically resolvable or just on the edge of it, but were things that were also being able to, were intervals that the geologist, in this case Mark Woodall, again, who's sitting at the back, was able to go and correlate consistently. We went and built into the model, what these particular intervals were in terms of their thickness as well as their net to gross, and then superimposed this with the seismic data. So this was used as sort of an initial constraint going into the model. This is, I don't know, Chris Haas, I think, characterized this like having a baby in terms of trying to build this in terms of it was fairly painful, but I always question, how do you know what childbirth feels like? But you can see here, though, for each one of these wells, we had what the gross thickness was. We also had what the net to gross was for every one of these intervals over which we built the model. And then we went and sort of, first of all, tested the inversion at each one of the wells by going and inverting and not telling it what the answer was, and looked at how well you were able to reproduce what the answer should be. This is what the answer should be. This is what it was able to find in terms of its answer. And you can see the uncertainty in the answer here. I was able to tell where the base of this reflector was. Probably wasn't that certain of where the top was. I was modestly certain of where the top and base of all of these reflectors were. I can't tell much once you get down around where the particular fluid contact is. In other words, you see that it's very good at telling what happens down to the fluid contact. Can't tell much below it. And that's because the sands here, again, become transparent when you actually put brine in them. In other words, wet sands look a lot like the shales do here. You can see, we call these spaghetti plots because it looks like a bowl of spaghetti. Okay. This was done in terms of both, we simultaneously needed to match both the near and the far stacks to within the expected signal to noise ratios here. And again, these are the synthetics of all the individual models at this point at Scarborough 1. Looking at what the net sand was, that before the inversion, it was fairly broad. It was was at 10 meters at this case, plus or minus 2.3 meters. After the inversion, the uncertainty was reduced to 1 meter, okay? And it's really whether or not you'd have this much or that much sand is sort of how we went in and built in the variation. I'm not going to comment on this. People are in the room. That we did have a lot of good to and fro and sort of questioning on whether or not, though, we did go and did the predictions of these wells for all these sands match what were in the wells, because we wanted to know what the sort of the calibration was of it. And what we also wanted to see was that the scatter of these points about this line would be about correct, as well as did they lie along the lines. There was one particular point where there could well be sort of a violation to the particular sort of model, some cementation or some possible slumping, so that what we saw at that point really was in the seismic was not representative of what you could actually see locally. And that's when Dave was talking about a wellbore seeing something this big, where seismic sees something the size of the room. You can't tell that much about the porosity in this case. If you're dealing with harder sands, you could tell and you'd see that there'd be a much tighter scatter with respect to the porosity predicted versus actual. We did correct for the particular shallow gas that was here, because what happens is the shallow gas was shadowing. This would be your background map, okay? And what we did was modulate the size of the wavelet by using this map. So you can do a background map correction, and that was done here. And this is sort of talking a little bit about the build of the model. We had these three major picked horizons along with the fluid contact. We built it. You can see with these particular layers and the net to gross of the layers. This is not sort of creep to what the well control is. We also built it saying that if you're well above the contact, we knew it was gas. Well below the contact, we knew it was brine, but around the contact, we weren't quite certain.
Was the model built on inverted data, like the spark spike?
It was built off the sparse spike inversion. Because really, in the end, if you can't see something on the sparse spike inversion, or some type of little, wispy, soft streak, don't build it into the model, because there's no magic. It's looking at the same data. After the inversion, you can see that you tuned up where you thought it was gas and oil. These are pathologies that came about because of thick layers near the fluid contact. And since then, we've corrected this problem that you'll see by those little spikes. This is what happened to the net to gross. This is before the inversion. This is what things look like after. You see that it's doing things like picking up this thinner high net to gross streak here. It also is picking up the fact there's a nice sort of thicker sand here, but less in this area. As we go, I'm just going back and forth. It's also picking up the fact there's only one thick, not two thick sands there. That's right, and I'll show that in terms of some of this salt and pepper, but putting in the lateral correlation ends up ameliorating that a bit.
That thin sand, you could see it from the well, right?
What's that?
That thin sand.
Yes, you could see it in there. I mean, this is the acoustic impedance of the model before and after. And you say, well, why is it doing that? This is the sparse spike inversion. And you can sort of see how we ended up deciding to build it at the scale that we did when you start taking a look at the impedance of it. But you can see that it's using that model and is recreating the sparse spike inversion, but now we have a lot more information about the models and the uncertainty underlying it. We also get the model in depth as well as time. You see that the fluid contact is much more well-defined in depth. You'll say at points like this where it has some uncertainty about where the contact is. It turned out the contact's going through sort of, quote, the middle of the shale at those locations. So it just knows that where it's a sand, it definitely is gas, but by the time it gets down to the next sand, it's not gas, but because it's a shale, it doesn't really know where the boundary is. And here is an example of one of the particular net sand maps in some of the, let's see, the upper fan. This is what the profile looked like before the inversion. That's what it looked like after. You can see that it had a fairly good idea of what the sort of the shape looked like here. And this is one of the major things that we wanted to tell. Also, if you look sort of closely, that where it finds sand here, it says there isn't sand in the other one, and so there's some evidence of a compensational structure, which would be expected. And then this is where you're saying, yeah, there's a lot of curtaining. And if you go and take a look at something like the amount of hydrocarbon, okay, column, you end up seeing that there's a salt and peppering, and that's what that curtaining ends up looking like in a map sense, okay? But also, we do know that there is lateral correlation here that isn't built into this because the inversion has been done on a trace-by-trace basis, okay? So what we ended up having to do is after the fact say that we want to go and build in this particular lateral correlation, okay? And this is what we sort of call the analyzer or massaging. You'll see why we're going to look like we gave us a nice massage and sort of got, sort of took away its nervousness and its sort of tightened muscles here, okay? And the way that we ended up doing that is to say that, okay, we know what the uncertainty is at every point, but we also know, if we can understand the size of the geologic structures here, how much the particular properties should be correlated, or they should be correlated over a particular range. Geostatistically, we call this what the variogram is. The range is kind of the geologic body size, okay? And the particular sill ends up being what the standard deviation is if you ended up going a significant distance away from that point. And if you, at the particular point ends up being if you actually had the well measurement at that point, okay, what should the standard deviation be? And so what we did is allowed there to be some structure in things so that we know if we're right at that point what the standard deviation is or what the, the nugget is. And so then as we move away with the range of the variogram, it should go back to sort of what the range is overall in the model. Yeah.
Can't you do this before this level, before you're extracting quantities back at your inversion level by just trying to line up the, like you look at the autocorrelation between pairs of these stripes, these vertical or one-day inversions, and just try and line them up so you get the maximum integrated.
You've just gone from a coarse grain to a fine grain distribution, and you've gone into a message passing inversion nightmare, and you've gone from 200 dimensional to 100,000 dimensional matrices you need to invert. Yeah. No, you're exactly right. It could be taken account of in the initial inversion process, but there's very strong computational reasons why that's not done. You either have to dramatically simplify the model to be able to solve it, or you have to go and wait until afterwards because it's not computationally feasible.
Is there any trend? Is there any trend to it?
Trend to the...
So you've looked at a cluster of points around as well.
That's right.
That there's a fabric to the geology.
Well, it turns out that effectively when we go and build in this lateral correlation structure, okay, with the inversion actually given by the seismic inversion, Okay? And you can see that if you take a look here, that if where each of the wells are, you end up having a little, you can go and if you look carefully at it, you have little tiny bullseyes around each of the well locations in terms of the variance. And as you move away from it, you go more towards the variance of the solution of the inversion. And you also end up always following and go to the trend as has been determined by your remote sensing information. So it's really blended the remote sensing information of the seismic and its uncertainty with the well information, and has also respected sort of the size of the geologic bodies in terms of the variance or which particular cells sort of move up and down together. But this is actually very important from a practical sense because the reservoir simulations absolutely hate something which looks like that, okay? Because they're trying to figure out derivatives, and that's dramatically discontinuous, okay? So they want to go and figure the derivatives of something which looks like that, not something which looks like that, okay?
That's not you.
And this is that standard deviation map you were looking at, and you should go and probably, if you want to reduce the uncertainty, site a well at the maximum point of the standard deviation.
So you effectively just low-pass filtered the previous image. And then
It is effectively a smoother. You ended up smoothing the data or the solutions with a sort of a smoother the size of the variogram. I mean,
so the frequency depends.
yeah.
Yeah.
But you have reason to believe that. You didn't build in the correlation. It's the correlation that's informing it in a straightforward way. Okay? This is what all the particular sand realizations could look like coming out of that. Okay? They're all consistent with the seismic data, and they all match the well control, and they match the seismic data not only to most likely value, but the uncertainty in it. Then you can go and integrate all of those maps in order to get a volumetric distribution or a resource estimate, and also a range in the resource estimates. We broke it up between lower, inner, upper, and what the total would be. You can get other things like porosity maps out of it. But what really, I think, is important is that then we go and can either go back into GoCAD or Petrel or Eclipse and bring in a model that will be on the unstructured grid, will be along the stratigraphic intervals that would be in there, will match and have the right net to gross assigned to the properties for each one of these layers. It will match the well control exactly in depth, and also will go and be consistent with the seismic data in between. You could bring in a model which is kind of the most likely with properties that tell you what the standard deviation and medians are, or you can actually have models which are like 5 or 6 models which are representative of models that you may encounter. In fact, you could have 1,000 if you wanted to, and bring those back in as very specific realizations of the models. And if you looked at that ensemble of models, it would have the right averages, standard deviations, and the like, as would be indicated by the inversion.
When you calculate these means and standard deviations, do you calculate means and standard deviations on your realizations and then blur, or do you blur and then calculate means and standard deviation?
It ends up being the former. Because we have to, in order to do this, we have to linearize. It's an assumption. Mark, do you have any particular questions? I mean, I can go a bit more into one or two things if you would like, actually, right now.
It was more just how you actually generate your any probabilistic maps like P90 and P80.
I mean, that would be after the
Coming out of the analyzer.
coming out of the analyzer. Okay. I mean, what we end up doing, and it's fairly simple, is coming out of the, coming out of the, we really have gone and generated one of these or an ensemble of these maps, okay, with the lateral correlation also built into it. And we'll go and add, if you want the P90 map or P10 map, we'll go and just choose a point and calculate, you know, out of all of these maps, you know, what is the high and the low at each one of these particular points, okay? And in order to calculate the volumes, we'll take each one of these pictures you've seen, calculate the volume associated with that picture, and just build up, you know, a frequency chart associated with the volume of every one of these particular movies.
Is that that's from each bin, is it? So each bin's treated in an individual way?
Well, we'll go and we actually integrate, for the integrated volumetrics, we will go and calculate the integrated volumetrics from each one of these pictures in a sort of a connected volume, okay? And we actually will look for a connected volume, okay? For just looking at the high and low side maps, we'll just look at a point and then look at what the high and low values were at that one particular point.
So then you would extract all the P80s or whatever it is at each individual.
That is correct.
So they might not actually relate to the realization that generated it.
That is correct, yeah. That if you go and take a look at the P80 at any particular point, things around it within a range would tend to look similar to it, but it'll eventually die off. And so, yeah, it is uncorrelated. And that's the reason why you see there seems to be a lot more flutter in these realizations than would be indicated looking at just the simple maps. I mean, I think that's what these people, the person sees this, okay, and sees this, they'll go, this is the median, and I'm just going to sort of flitter this, but it always is going to look like this, okay? You don't realize that if you have to go and keep something that's about this size, and this is your standard deviation, that even though that's the most average, you know, all of a sudden you can get a lobe coming over here that's just sort of, you know, not, or something happening here that isn't even there on a different realization. Because everything is sort of going up and down together. That's why I think sort of, you know, sort of P10 or P90 maps just by themselves are, can be different than if you go and significantly different than if you just go and ask what does each individual realization look like. Okay. Yeah.
The analyzer and the massage things seem to be different. The result, does that mean the analyzer only produce one realization?
Well, it turns out, I mean, that the analyzer and massager end up being, they're the same thing. The analyzer does the massager. And also sort of includes what we call the decoration step too. So there's a massaging and decoration that are part of the analyzing steps. Well, let me just go back. I'm sorry, I probably misspoke. Let me go back to the diagram here. 3. That you're right that the analyzer ends up preparing things for the massager. The analyzer prepares those statistics that you were talking about.
Error correlation.
Okay. What?
Yeah, error correlation.
Yeah, yeah. The means and standard deviations of everything. And the massager then takes that and sort of generates the realizations. Given the results of the analyzer, and also it has to go and have some extra information about the variogram or the correlation lines.
Where does that variogram come from?
It comes from asking geologists what are the sizes of the characteristic depositional bodies that you're using. We do also sometimes go, well, most of the time, we'll go and do a more standard variogram analysis off of an extracted amplitude for that horizon tube and try to understand the consistency between what the geologic body depositional sizes are and what the sort of the variogram structure is of an extracted amplitude.
But does the sort of the range in the sill that comes from the statistics that you're out of the inversion that the variogram?
That is right. Yeah. Yeah, that's right. Yeah, and then that's so that the range in the sill ends up coming out. Those are the explicit numbers that get tied coming out of the inversion.
If you get the wavelet wrong, or fail to pick a good wavelet, then you overestimate the signal to noise ratio, right? Because you treat mismatches as zero.
What's that?
If you get no.
Well, if we do what? State that again.
If you get the wavelet derivation wrong,
Yeah.
and then you're deriving a signal to noise ratio from your match, from your well type.
That's right.
So you now overestimate the signal to noise ratio.
Well,
it's correct
the
for that
noise.
wavelet.
Well, you get a signal to noise ratio which is less than what it should be, is what you're saying. Right? What do you mean you overestimate? Is the statement that you think that the signal to noise ratio is better than what it should be?
You overestimate the error. Yes.
You
get a
overestimate
signal to
the
noise.
error.
So
That's
now
right.
you underestimate the amount of the probability of finding sand because you have less information.
That is
with
right.
which to constrain that. So if you get the wavelet wrong, you have a systematic underestimate of quantities.
You end up, well, you probably won't bring in a bias. You have a systematic overestimation of uncertainty.
Yeah.
You have and you may well, with the wavelet itself, build in a bias if the wavelet is incorrect. Yes. I mean, doing good wavelet derivation is very important to this. And overall, whenever you do an inversion, as Long probably has found out, getting the wavelet right is very important, and you have to spend quite a bit of time making sure you get it right. But that being said, you do, there are simplifications in the model you use, and that's going to cause you to go and have a larger uncertainty, because that particular uncertainty also includes not only true noise in the data, it will also include the fact that you didn't use the right model, or the model isn't totally correct.
And it doesn't just change it. I thought it doesn't just change your error because you figure out the probability of there being oil there based on how well you can separate these things.
Mm-hmm.
If you make the error larger, you actually reduce your estimated probability.
That's right.
So it doesn't just change the error; it changes the mean.
Yeah. Well, yeah, if you look at it as a bimodal distribution, that's right. Okay, let's just go and sort of move on then. There's, as I said, I'm not. This is not meant to make it so that you're, experts in going through the. Going through the process, but I also want to go and bring you up to speed too, is that we also go and have the ability, and there's a lot of value many times, of just looking at this at one sort of prototype well location, okay? Instead of going in and building this model over the whole field, if you have like a characteristic point at which you're trying to characterize, your particular prospect, I'm not going to go into this because I want to make sure that we can sort of get on and get through the other things that we want. We do have, go and say that you don't need to go and build the whole model. You can just go in and look at a prototype location. In fact, it was John Cant down here in Australia for Santos that realized, I think, at first the value of just looking at a location. And it's been used in a couple places here, I think, Crosby and also we looked at the Glen Ridden well too with it. And I'm not, And also, I think at one point I did talk about one of these particular sort of porosity inversions. And here, we actually did go and ask the question on whether or not this was a good or bad porosity rock. And so you can go and do these things in order to be able to tell what the porosity is, not only what the fluid content is. Okay. And the other thing is that we've also built up a nice little interface so that you can go and sort of build up the layers of your models, go and assign some of your basic properties, enter in your trends, similar to what the spreadsheet is, and then hit the go button and then take a look at the results. This has been built up for what we call the delivery light. We're just looking at a prototype location, and within this fiscal year, we're going to be, the plan is to extend this so that it facilitates the building of a more complete model. Okay. The other thing I wanted to go and at least make sure that you guys were aware of are things around wavelet decompositions. And I'll tell you first, what are the inputs that we need and what are the products that you get out? Well, you need just seismic data, pretty much any flavor of seismic data. Key stratigraphic horizons for flattening, you'll see end up helping with the interpretation. Having sort of just a coarse idea of what your average velocities are for the sections you're interested in are good. The products are an interactive session showing the decomposition in color versus the seismic data, along with flattened maps of the decomposition. You can have movies of this stratigraphically flattened decomposition, which we'll show you. And also you can have sort of interactive sessions showing the bed scale. And these also can operate directly with Landmark, putting certain types of this data back into Landmark, because Landmark itself is not a pre-stacked data viewer. And so we end up working outside of it. But let me sort of talk a little bit about wavelet decomposition and some of the value associated with it. What you see here is a derivative of a log row V trace of a piece of a well log. And what I wanted to go and say is that, you know, this to me is a bunch of wiggles. Is the top different than the base? I don't know, I can't tell. But what you can do with these particular techniques is to take this and decompose it into what it looks like at different bed sizes. In other words, that at this particular larger bed size, which is this large, you see that we end up having sort of beds of this size all the way from the top down to the bottom. If we go and look at beds of this size, okay, this is the bed size axis. Beds of this size, which are these little beds, we only see those little beds at the base of this package. I know it's pretty hard for me to tell that's the case. And then if we go and say, okay, well, what happens when we put the seismic on it? Well, that ends up being, you know, the seismic wavelength, okay? And so you end up going and, you know, for as near as you can tell, this comes from the top sort of loop. This ends up coming from the base loop, okay? And so I'll show you in a second what it looks like with respect to the seismic itself. If we shoot seismic through this and then take a decomposition of it. But what's kind of interesting, and the reason why that I think that there's a good amount of value in this, is if you take a look at something like the Dendara M7 and the Chinook Marl, it turns out both of these end up having about the same reflection coefficient. But Dave talked about a nervous sand deposition as described by Rufus LeBlanc. If you go in a complicated picture means that you're nervous, okay? This looks like Captain's, you know, hook. I'll show you something else that has blobs all over the place. And if you now go and look at this is fairly simple. It's just a blob like this, or this is a less nervous deposition. Now I challenge you to look at this being the blue line and that being the blue line and say the stuff on the right is less nervous than the stuff on the left, okay? And the interesting thing is when you look at the seismic data, you see the same patterns in it, okay? And this was actually fairly poorly processed spec data, by the way. And when we've gone and taken a look at sort of the average bed size and sort of the range of bed sizes on this, we've ended up seeing, if you look again at a whole bunch of points that are taken from different well logs, of sort of what the variation is in bed size versus the average bed size, we saw that different type of rocks tend to exist in different parts of this space. So if you see something like a particular Chinook marl, you see that's clearly in the marl one. And you could look at the particular Dendara point, it's clearly in the sand one. There's obviously some overlap where it could be either, but these two things definitely lie in either the blue or the red sort of clusters. For this point of view, I'm not considering limestone or thin sand. But if you did consider, though, thin sand, we know that Dendara could not be a thin sand, but the Chinook, it could be that marl, which it was, but it could have also been a thinly bedded sand. So you could have made a mistake in this case if you didn't consider a thin sand and just sort of interpret Chinook as having to be marl, because it also is just modestly consistent with what a thin sand would look like.
Is that the relevance to the risking spreadsheet?
Yeah.
It's a reservoir characterization.
Yes, right. And you see the spectral decomposition, if you look carefully in the risking spreadsheet, it only influences reservoir probability.
So where did these blobs come from?
They came from looking at a bunch of wells and spectral decompositions of the wells. Yeah. Because we had a lot more wells in this area than seismic because it's subsoil. And also I wanted to go and sort of show you some other ways that you could sort of understand things about the geology on this. This ends up being the hockey stick, okay? And if you look at it and think about it for a bit, it means that the beds at the top here, as you go towards the top, end up getting smaller than the beds at the bottom, right? What is that? That's normally what we call geologically a finding upward sequence. And if you looked at sort of the net to gross profile, that you see that there's a fairly classic finding upwards levee progression where you see that you get fewer and finer beds as you move up towards the top, okay? But if you looked at that seismic wiggle, it really looks like a reflector, and it would have been fairly hard to tell looking at the wiggle, because I did, that you ended up getting this particular complicated behavior. Also, when you ended up getting something that was sort of blocky like this, you end up finding that it ends up being one of these nervous patterns of three different blobs, one associated with the package size, the other associated with the sand package size, and the other one associated with the size of the shales that were being interbedded with it. Okay? But again, here, nervous means complicated in terms of what's going on. And so how do we go and sort of take a look at this stuff? Well, one thing that we do is to go and take a look at, here's the seismic data. It's shown as the wiggles. Behind it, we see the spectral decomposition, and we're looking at a very specific bed size. That's an 80-foot thick bed size, which is what, about 25 meters thick, okay? If you have a lot of beds of that size at that location, it will be red. If you don't have any beds of that size at that location, it is blue. And so you can see that right here, there are probably more beds of that bed size here than here. So that this particular reflector probably is associated with sands of about 25 meters thick, this is either less or more, but it's definitely not 25 meters at that particular point, okay? Then what else do we end up doing? Well, this is kind of hard to understand just by itself. And so we'll go in and stratigraphically flatten this so that once we stratigraphically flatten, time in this section ends up being equivalent to geologic time. So something right at a constant time here ended up as close as we can make it to being laid down at the same geologic time. And then you can also go at, let's say, a particular point, which is this point here, go and look at what the particular, what we call frequency gather looks like, or in other words, for this particular trace, this is what that looks like as a function of bed size. And then you can look around and say, oh, the bed size here that really matches the best is this particular point right here that I'm pointing at. I'll look up and, oh, maybe it's actually even a little bit thicker at that point, and I hadn't even reached the maximum yet, and I actually wanted to move out to here. And then if I wanted to go and tell what the bed size would be here, I touch this point, and then look at this particular picture, and you probably would see it would be a bullseye that would be here at a smaller bed size. Okay?
Mike, how do you, is there a requirement to flatten the data before you run wave of decomposition on it?
No, we actually do the wave of decomposition and then flatten it. So you can look at all these gathers. You know, you can look at this picture, you can look at this picture without flattening. Okay? The advantages that end up coming about from the particular flattening of it come about when you start looking at things like the flattened slices.
Yeah.
And I'll show a couple, I think I have in here the movies of that. I'll show in a second. Okay. But I need to click, I'll click on these QuickTime things. Because what we can do first is say at a particular scale, I'm going to go and just scan down through here at a particular scale and look at those maps in those stratigraphically flattened sections. And you can sort of see, this is sort of like a little tour through the geology. You can sort of see that things will be sort of moving from they sort of move from one side to the other. You can sort of see at particular levels where you can see a channel come through at particular times. And then in the base one here, you actually can sort of see when the deposition came down and another channel cut through it. And let me just sort of go back and forth a little bit. And there's another thing I like, is you can sort of again go through and you see how the deposition center goes from one side to the other as I go back and forth here. Also right here, you can say, oh yeah, you can see where the particular channel and the overbanks were at this particular geologic time. And then if I go down, okay, not much happens here, it's quiet. Then all of a sudden I come into this little complex. Right here I'm kind of in the center of it. You can see the meander, the little levees on either side of it. And then if I go down to the lower section, you see where you'll have sort of the main deposition, and then also there's a channel that actually cut it off and actually formed part of the stratigraphic trap at a later time here. And what we found, though, is that if you're going especially into a new ventures area and want to go through and have good data where you can sort of pick good sequence boundaries and stratigraphically flatten something like this, it's a great way to very quickly go in and interpret something. Because what it first came about when I was working with Roy Fitzsimmons on the Platforma Deltana farm in, that I formed one of these cubes going from the top to the base of a fairly large sequence, and that Roy just took that movie and spent probably a good hour with it, and then capturing some of the key horizons and got a really good idea of what was happening depositionally at each one of the times. Okay? And it turned out too that it was much easier to see the geology, within the spectral decomposition And in fact, I'll show where you can actually have a movie at like 3 different scales and see what the geology sort of looks like at 3 different scales as you pan down through it. You say, well, you might also though say, well, what, why even go and do this scale of this sort of decomposition? And this is just one particular geologic time, but it's what it looks like at different sort of bed sizes, okay? And if we're going to go in and sort of, try to tell what's going on, it turns out that this bed size is actually best at seeing where the fluid contact is. There's actually a drape over, there's a high here, it goes down on either side. There's a stratigraphic boundary of a channel cut here and here. And it turns out that this is at the same depth as this on each side of this sort of nose. But it's fairly easy to go and see at this point. But then you'll say, okay, what's causing the boundary on this side? Well, if I go to a little bit larger size, like right here, now you can't go and see this fluid contact, especially here or here, but you see very clearly where the channel came down and cut into here, okay? And so, depending upon your bed size that you're looking at, you can highlight different features in the data. And it turns out that that includes the fluid contact as well as sort of different sort of geologic processes that may be happening. Okay? And it turns out that there's sort of an old blurry way of doing this and a new sort of high resolution way, my glasses before I got my new prescription and after. We do have the programs to do both of these. Why don't you always do this, you may ask? Well, it's a lot more expensive and takes longer to do, is the primary reason why. One last thing, and this is sort of interesting pieces of the toolkit sitting up there that you may want to sort of know about, and this is the last sort of interesting piece. It has to do with, it's a use of a satis. It's something that's probably used much more in mining than it is within petroleum. And many times we want to know what the structural uncertainty is, or could we close, or what's the uncertainty in the depth conversion, okay, is another way you could be looking at this. And we end up, what are the inputs to this? Well, give us key horizons, give us estimates of the imaging velocity uncertainty. Well, how do you get this? So you go mark, okay, how much, could you change the velocity and still keep the gathers reasonably flat, okay? Okay, that's how you get the answer to that question. You also estimate sort of the geologic body size and orientation, okay? Why? Well, we need a variogram, okay? And that's how we get the variogram. What are the products? Well, we have realizations of the structure and pore volume. We have probability of closure maps. We have mean pore height maps. We have volumetric distributions and distributions of spill points. So we know where the critical positions are in terms of defining whether or not the structure closes. And so, okay, what are we going to go and let me give you a little example of this. Well, we ended up, in this case, we had a top structure map. We ended up estimating and talked to the geologists and also analyzed did a variogram analysis of the amplitudes in order to be able to come up with what we thought the geologic body sizes were. We did know and separated things out in terms of 2 extra ISO packs associated with a forereef and the main reef facies. And then sort of then asked, okay, let's go and look at, first of all, what's going to be, within our little dome of structural closure here, because there tended to be a spill point over at this location. We also ended up having another one that said you either did or did not seal against this fault. There's two different scenarios. And what, first of all, is sort of the gross amount of area within closure, and then what is the net pore volume within closure. And oh, by the way, this was actually a case, this is a carbonate, obviously, and there was a different, distinctly different reflectivity here than here, and it's associated with the higher porosity in the oolitic fore reef, okay? And we actually did have predictions of porosity again for this case. These are the realizations of exactly how much column height we had, or the sort of the distance from the contact up, and you also see where the spill point is in that for each one of those realizations. We also could go and say what is the amount of pore volume we have, and we also could ask what's the connected pore volume here, and that would be how much volume we had. Then you can have the mean height above the spill point, and you also saw where all the spill points were. Okay? Since you knew that the critical trapping element is sitting over here, that ended up leading us to go and buy a lot more data sort of subsequent to this analysis in this area in order to be able to refine this critical element, because we knew this is what was sort of causing the particular uncertainty. Okay? And also, there's another particular map, which this is the probability that you're above the spill point, okay? And this is sort of the mean pore height when the fault is sealing. And so what does this mean? Well, this ended up being in size about 50 OCS blocks, so you can bid differently according to sort of, you know, each one of these little blocks. Mean pore height sort of ends up being proportional to sort of value in this case. You also could take a look back at the probability that you actually are in closure also is another good thing to look at. And actually, if you looked at what our particular bids were on these blocks, it ended up being roughly proportional to the color on this map. Okay? And it turns out, though, for those of you, we actually captured this whole structure pretty much in the last Eastern Gulf of Mexico lease sale. But what I really wanted to go and let you know is that there are ways to go and risk structural closure or understand uncertainty in depth conversion. And for instance, if you went and had a probability of closure map, okay, here, if I went and saw, let's say, my contact meander around this yellow zone, I would go and probably say that would be okay. If I saw an amplitude that actually went into the red or went back out into the blue, I would start becoming worried about it, okay? So it's a way to sort of test, sort of how good do I really know what that particular sort of depth contour looks like, and sort of how much could I be going to the left and right here, okay? This ended up being a modestly sort of shallow structure, and so we really were worried about, what the particular sort of uncertainties were. Also, I didn't show here, but one of the things was a standard deviation map in terms of pore height, okay? And that, or in other words, in terms of, it showed you the uncertainty and how much volume could be there, okay? Do I have any suggestions in terms of how that could be used? If I had an uncertainty in how much volume was there? Whoa. Go ahead.
When it comes down to bids, if you're uncertain on a particular area, you'd low grade it on that bid.
It could be. What happens if you were trying to consider where you'd put a well? Where would you put the well?
Your exploration well would be on your certain area, and your appraisal well would be in your more uncertain areas.
Good. That's good. Okay. I think it's very well spotted. And so that you go, and as you go out to appraise it, you want to reduce uncertainty. That's correct. And you want to make sure the first one is in a certain point so that you can tell whether or not other things have failed. And that's just ended up being the volumetric summaries coming out of it. Let me just go, and I'll just go and summarize this right now quickly for you. First of all, what's important? That first of all, you use the quantitative interpretation phase 2 when you have these complicated models or uncertainty is needed. Wavelet decomposition is a useful technique. I think it's going to be interesting too, let's say, Ian, whether or not certain, is there a spectral decomposition fingerprint to certain type coals? I mean, it's just an interesting question that comes to mind that may be related to a depositional environment or maybe even a certain diagenetic process having occurred. There also are geostatistical techniques to help you estimate structural uncertainty or how much uncertainty you have in what your fit to structure should be. Okay, and don't be afraid to sort of use those tools.
We look at wavelet decomposition as an aid to identifying volcanic zones or volcanic signatures.
We have not done it. That's a very good suggestion.
Sorry, this is back a long way. Back to the risking spreadsheet. You sort of determine the coefficients in terms of how you do this Bayesian update via sitting down and with a group of experts, essentially, and putting consensus. You could easily also determine those coefficients by simply looking at regression of your success versus you have a whole bunch of past cases where you had different qualities of data, you've had different amounts of structural uncertainty. You could determine the coefficients from the linear regression.
That is correct. You tend to suffer from not having a lot of points. Over 5 years we got 20 points. So, I mean, larger companies could have a couple hundred over the same.
Can we get their points?
No.
No.
They won't tell you.
Well, you can go and try to get. Well, if you went up and asked them, could I have your points? They will say no.
But if you say, can I have your success or failure versus the quality of your seismic data, that doesn't really cost them very much.
Yes, it does.
Does it?
Yeah. But you can go, I mean, that being said, there are ways and industrial databases and, talking to people and the like that you can build that up. There also are some particular industrial consortia that are sort of aimed at everyone's sort of throwing in their raw information to build up their statistics. And so there are ways of getting at it. But you have to really think, how do we get enough points to do it? Properly quality controls. Because also the way we analyze stuff and have stuff tagged isn't the way Exxon will have it tagged. It seems you can get it. Information. Okay?
The other thing on wavelet decomposition, you say it doesn't really matter what data you, whether it's gold standard processing or ozone or inversion or things like that. There must be, at least at some level, there's, the ultimate spectrum of the data must come out in the spectral decomposition.
Yeah, I mean, if you really started playing around with the wavelet and the like, I had a good talk with Stefan Malott about this. That it, and I should go and go back to him and really document this. But it's fairly well known that some of these particular wavelet decomposition properties end up being more robust metrics than something like amplitude or exact global phase. That the basic shape of them are much harder. It's much harder to destroy a dominant resonance in a system. Yeah. And I think the best way, those of you who are aware of control theory, that there's what's sort of considered how many poles are in the system, and it's sort of a topological invariant, okay? And that those things are very hard to destroy. You can move them all over the place, but it's hard to destroy the particular existence of it. And in fact, it's been looked at sort of ways in terms of doing quantum computing by Microsoft even, is to sort of look at topology and conserve topology underneath measurement for that. So I think that it ends up being a much more robust, sort of geometric, sort of oddly geometric quantity of the reflector, and isn't dependent upon small details of exactly, exact phasing and the like.
Have you compared running the spectral decomp on different data sets, like the original spec data compared to reprocessed?
I mean, have we done that with Sky? We did try a lot of different, sparse spike, and we, Long, here did a very good study with Guy's help about, doing it run some, not run some, Wiener decomposition versus, deconvolution versus sparse spike, and really found that it was fairly invariant to that. And also, I mean, I think we have looked at a more recent data set over, let's say, Cascade and Chinook, compared to what were there initially, and the decompositions look substantially similar.
Maybe you see what the Scarborough looks like, the original, and the stand.
If you increase the bandwidth, you will see, I don't know if you noticed on that one on the data, it did tail off at smaller bed size, and then and as you increase the bandwidth where you're above the signal to noise, you will push that back and see more of the spectral decomposition. But what you can see, what's in the passband, ends up being relatively invariant. If you make a bigger passband, you just see more of the picture.
Yeah, but I'm just wondering from a processing point of view, should we push for as broad a band as possible so that it helps QI or helps the spectral decomposition, or with spectral decomposition see it anyway if we just leave it alone?
Well, what matters is signal to noise ratio. I mean, if you go and do something to the image that enhances the bandwidth over which you get possible improvements in signal to noise ratio, that should always be done.
Yeah.
If all you're doing is boosting the high frequencies and boosting the noise at that frequency the same amount, that's not going to help the process.
Okay.
Is the easiest way to say it.
Is it dominated, this flattened spectral decomposition slides, they're dominated by dominant frequency, such that when you look at the high frequency slice like a 30 hertz, is it dominated by something down to 21 hertz?
That's a really good question. It's one thing that Guy and Long took a look at, that if you go and look at the raw spectral decomposition, it will be dominated by the wavelet spectrum and be highly colored by the wavelet spectrum. There's kind of the idiot's deconvolution, which ends up being the best, which is just to take a look at the average spectrum over the whole data set at a fairly broad range of times, figure out what that is as a function of frequency, and then effectively divide by it. I mean, it's like an idiot's Wiener deconvolution, only in amplitude. That ends up, as it turns out, is the best thing at restoring the spectrum, and Long and Guy found that they ended up getting fairly good correlation to where the peak was in the frequency versus what the bed size was of the sand after they did this idiot's deconvolution.
That's the one I worked out, was idiot's deconvolution.
No, that's I think I probably.
Well, you restore the color.
No, I'll claim this idiot's method. I'll be proud of the idiot's method. But yeah. But yeah, I mean, that was a really good question. And I don't think that this particular little trick isn't commonly done or sort of known in the industry. It's sort of done by what the Landmark package does. They do something sort of close to it.
But we do that when we do.
Yeah.
When we go through this.
That's right. And in fact, I'm going to go and start you on exercise right now. And the underscore NORM or the underscore norm means we've done the idiot's deconvolution too.
You're going to read the lunch and nobody will want to. Don't they have cakes over there and stuff? Damn, they might. I don't know.
Okay. We'll break for tea, and probably at about 5 till I'll give you sort of some instruction for the next exercise, exercise 8. Okay.